First of all, thank for the invitation and thank for the national team of German. I'm not going to tell you most recent data. I'm going to tell you the outcome of the long stay of Henry Foreman in my lab last year, and after that, the long discussion with Kelvin, with Matilde Majorino, some other friends, trying to figure out something going on in this area of free radicals. And basically what we tried to do was to summarize, to distill some information, some notion, after almost, unfortunately, 40 years in this field. Well, the area of the free radicals has been interesting for nutritional, people in nutrition, people in chemistry, people in medicine, people in oncology. And then what came out was this kind of concept that free radical, that eating food and vegetables is very healthy for you because there are a lot of polyphenols in fruit and vegetables that protects you from a lot of diseases. And this makes sense on the light of a notion that nutrition in humans evolved in three major areas. For the first time, 10,000 years ago, it was important to get the basic nutrients. The energy was the first element. After that, in the last 50, 60 years, basically due to the job of our colleagues biochemists, they discover the vitamins, oligoelements, and so on, and then they recognize the deficiency diseases. Fine. And now we have to deal with molecules which are not essential. They do not produce a deficiency syndrome. They don't cure practically anything, but are supposed to help in decreasing the incidence of diseases. And the story is so strong that the American Cancer Institute, National Cancer Institute, said the antioxidant protects cells from damage caused by unstable molecules known as free radicals. This notion was so popular that it was also quoted by Jan Fleming in a famous James Bond movie already in the 57. Free radicals are supposed to do something bad for you, and the only thing to do is to be protected by antioxidants. Again, the National Cancer Institute said that antioxidants neutralize free radicals as the natural byproduct of normal cell process. Free radicals are molecules with incomplete electron shells which makes them more chemically reactive. Antioxidants are describing making up free radicals and so on. Come on. We could not accept for a student in chemistry, on biochemistry, such an oversimplification. And then we decided to think, how is possible that an important institution like the National Cancer Institute reached such conclusion? Basically, what was built up was a kind of syllogism. In the syllogism, you have two notions, both true, but taken together produce something that, according to Aristotle, was a synthesis and sometimes is deeply incorrect. The thesis, true. We know for sure that oxidative free radical reaction damage biological molecules. We know hydroxylation based in DNA. We know the formation of carbonyls in proteins. We know lipid peroxidation a lot, almost 1.5 century. The antithesis is that there are plenty of polyphenols, usually extracted from exotic plants, that contain ortho and para-hydroquinone group that are competent for free radical scavenger. There are a lot. Somebody calculated something like 20,000 papers in the last 50 years. There is no question about that these molecules went free radicals. The synthesis was rather obvious. Free radical scavenger, nutraceutical phytochemical, protects health by scavenging free radicals in vivo. And this concept was accepted also by the National Cancer Institute, describing the mechanism. Do this make sense? Most likely it's just wishful thinking. The syllogism do fit the chemical evidence vaguely. What is the epistemological bias? Well, going on deep on these things, we realize two notions that we would like to share, to discuss. First of all, the notion of antioxidant is a relative concept. In this scale, you have the reduction potential from the bad guy, hydroxy radical, to the good guys at the other side, ascorbyl, and the semiquinone radical, tocopherol radical. Everything is relative. Each of these couple is antioxidant versus something on top, and peroxidant versus something at the bottom. Where do you put the line? For instance, the TL radical is a couple that protects, or is a couple that propagates peroxidation. This is the first part of vague definition of what we want to know about free radicals. But even more importantly are the kinetic constraints for an antioxidant effect. Let's start from radicals, and then we look at the possible radicals involved, antioxidant involved. First of all, hydroxy radical reacts, everybody said, 10 to the 9 with everything under the sun. Forget about. Practically the same for the alkoxy radical, 10 to the 7, even up 10 to the 8. In order to protect the damage generated by these molecules, the only thing is reducing the peroxides from which alkoxy or hydroxy radicals are produced by electrolysis of O bond. Then the antioxidant is everything but a free radical scavenger. Second notion, carbon central radical. The additions 10 to the 9 to the carbon central radical. By no means there will be an antioxidant quenching. I'm sorry, a few minutes ago, I'm talking about physiological conditions with such a rate constant. I do see extremely hard to have a free radical scavenger reacting with carbon central radical, competing with oxygen, at least in the presence of oxygen. Third one, possibly the most realistic. Here we have a kinetic advantage. Hydroperoxide radical, and this means that we are only talking about lipid peroxidation, not in the bulk phase, in the membrane, because the bulk phase is a different story. These peroxide radicals are relatively not so fast in reacting with lipids, 10 to the second to the third, whilst tocopherol reacts much faster with the same chain propagating radicals. This is the story of Keith Ingold of the chain breaking antioxidant. The story fits perfectly. We have 3 order magnitude of difference in the rate constant, and then tocopherol can be a free radical scavenging tocopherol radical working only in membranes when there is a peroxidation chain reaction. In other words, there is no chemical rationale in discussing tocopherol protecting proteins or even worse, nucleic acids. In the last equation is shown something that several people, including ourselves, including Roland Stoker, showed as something paradoxical, which is not paradoxical at all. If there is no competition, tocopherol radical can propagate peroxidation, but it is very slow. But slow, there's something else which is stopped at all, means that you can generate peroxidation from tocopherol. No surprise. If this is the concept, let's go to the biology. What can we conclude from having analyzed for 20, 30 years the mechanism of protection? The polyphenol can only play a chain-breaking antioxidant activity, just tocopherol, that integrates the effect of enzymes, but being limited by absorption, fast metabolism, and so on, cannot work if it doesn't reach a concentration up to more than 10 micromolar. This means never. Second, in the cells, the antioxidant defense is practically sustained only by enzyme and nucleophilic substrate. It means this is glutathione and thyroidoxine. No free radical reactions. This is particularly amazing that if you look at the textbook of polymer chemistry, the antioxidants are classified according to a mechanism which is the quenching of antioxidant hydroperoxide radicals, no other radicals. And this is one transition. And the second mechanism is the reduction of electrophile, typically hydroperoxide, by a 2 electron transition through an SN2 mechanism. And this fits exactly what happened in real life, because beside the superoxide mutation, there are no free radical scavenging reactions in the cells. Ready to discuss about this. And the biological active antioxidant active in vivo are a nucleophile that eliminate the electrophiles largely by enzymatic reaction. In the end, chemical mechanism is only an S2 mechanism. Notably, also the free radical scavenger somehow, like vitamin E and SOD, produce hydroperoxides. And the only way to get rid of the peroxides is to work by nucleophilic displacement reactions. Thus, the endogenous antioxidant system is activated, we know, by electrophiles, and it increases the nucleophile tone. In other words, there is a kind of adaptive feedback mechanism where the electrophile, the oxidants, are the only molecules competent for activating endogenous antioxidant mechanism. In fact, the electrophile is sensed by KEAP1, again by SN2 mechanism, and this relay releases the nuclear factor NRF2, everybody knows, and this activates the promoter for gene coding for antioxidant system and substrates. The drawing is a nice one. KEAP1 and NRF2 arrive with an electrophile. It reacts with a particular reactive cysteine. Then the electrophile also activates AKT PK delta, which phosphorylate NRF2. KEAP1 goes, hopefully goes, and NRF2 goes to the nucleus, where it activates the release of the synthesis of glutathione, synthesis of redoxic, synthesis of the reductases. In other words, an antioxidant system based on nucleophilic displacement reaction, no free radicals. What can do the phenolic antioxidant? I have to remember one evening in the Stockholm, in the house of Paul last semester, with Paul Talalay and Dr. Pickett, when they were commenting for the first time some experiment of some rats overload of phenolic antioxidant. Everybody expected a decrease of endogenous antioxidant system. Just the way around was the maximum stimulation of the endogenous antioxidant mechanism. This story has been rather clarified in the last years, when it's been clearly shown that phenolic antioxidant generate by autooxidation the electrophile that activate what they call IRE, antioxidant response element, now more precisely a PRE, and that produce the nucleophiles and the related enzymes. Let's look at the reactions. The reaction is the reaction of an electrophile with a reactive cysteine, and this is a typical microaddiction. Who can do this reaction? Well, first of all, some hydroquinone in the oxidized form, and more specifically, talking about plants, we have the hydroquinone, the plastoquinone of the plants, that in the oxidized form generate an carbonyl alpha beta unsaturated. The carbonyl alpha beta unsaturated is a typical molecule that interacts with sulfur, the sensor sulfur of the KEAP1. And here we have several examples. This is a plastoquinone for all photosynthetic plants. Here we have the carnosic acid from rosemary, the reduced and the oxidized form, carbonyl alpha beta unsaturated. This is the hydroxytyrosol from olives. This is sulforaphane by different mechanism from all the cruciferae. And more interesting, just to give an account of the mechanism, these synthetic or non-synthetic molecule that also are strong activators of KEAP1, of NRF2 through alkylation of KEAP1. The ethyl ferulic acid, ferulate, the methyl fumarate, and the hydroxynonenal. This links the story of lipid peroxidation, where it is clearly shown that a little bit of lipid peroxidation is good for you, because there is nothing better than hydroxynonenal, a product of lipid peroxidation, to enhance your defense system. Remarkably, I want to quote another molecule, really surprised me at several meetings, where the people showed that the healthy conjugated linoleic acid, which is a product present in dairy products, a compound present in dairy products, is an antioxidant. By no means that molecule be an antioxidant. Well, it has been clearly shown that conjugated linoleic acid, to the same mechanism, activate KEAP1 and release NRF2. In conclusion, the nucleophilic tone is activated by this electrophile through a kind of adaptive mechanism. And as a matter of biology, the nucleophilic tone seems good because it decreases the biological efficiency of practically all the hallmark of chronic degenerative disease and carcinogenesis. But in order to do that, our oxidant must fit some kinetic requirements to be active. Definitely, these our compounds, let's say the carbonyls, alpha, beta, unsaturated, or something similar, but these are the most typical molecules. They must react with the cysteine with a rate constant, usually faster than the rate constant of the cysteine not specifically activated, and the requirements for the activation of the cysteines in the target are the low pKa, possibly the polarization or stretching of the OO bond, and what could be important in some reactions, the protonation of the leaving group. This mechanism based on tire signaling has been summarized in a review I had with Henry Foreman and in the masterpiece in this respect, which is a review. No, 4. I have here. Wrong. I want to quote the review of Professor Floé about the signaling through redox systems. I go quick to the end of my story. I escape the oxidation. I just wanted to summarize what has been widely described in several reviews, and I'll quote again that by Leopold Floé and Regina Brighelio Floé, about the redox signaling of different targets that undergo a redox signal. And I would like to stress that this redox signal is involved not only in cancer, but in the physiological condition, in wound healing and embryogenesis. HAF1, metabolism angiogenesis, P3 kinase, ERK and FKB, and CSARC. For all these, there is an evidence of an activation by electrophiles and the counteracting mechanism by the nucleophiles. The overall scheme we propose is then the agonists usually generate of activating this signaling pathway, activates the formation of electrophiles. The activation of these electrophiles is targeted over the accumulation of some specific reactive cysteines. These give rise to an activation of tyrosine kinases, inhibition of phosphatases. In the outcome is proliferation, survival, metabolism, angiogenesis, and staminality. On the other side, the formation of minimally reactive electrophiles by the autooxidation of the so-called antioxidant activate the switch-off mechanism, peroxidase, glutathione, thyrodoxine. In conclusion, there is an innovative target emerges in preventive medicine from chemical nutritional studies that counteract the counteraction signal transduction pathway leading to proliferation, angiogenesis, and to escape the necrotic death. The leitmotif is the effect of phytochemical generated by oxidation of electrophiles competent for the adaptive increase. We call adaptive increase the fancy nucleophilic tone. We call, quoting these two guys that already spoke about hormesis, a mechanism of parahormesis where the toxic molecule just mimics the effect of a toxical compound. All this story, I do some advertising of a next paper already in press that summarize all the analytical, critical discussion of the analytical evidence we have about this. A funny story, just added yesterday, is that tomorrow there will be, tomorrow we start a meeting on polyphenols and antioxidants in Berlin, and the funniest, yesterday there was a press release for immediate release in Bonn, it's Bonn, it's not Berlin, wrong, where the author said, we believe that rapidly the term polyphenols will replace the banal and less credible term of antioxidants. In other words, also in the meeting in the Germany starting tomorrow, they are being aware that the notion of antioxidant or peroxidant has to be revisited in a way to have more compliance with the basic chemical background. Thank you.